Literally hundreds of millions of dollars of grant funds have been wasted trying to follow this story up. Something was rotten with resveratrol. We tried different suppliers of resveratrol, different forms of resveratrol. We tried it in the light, out of the light. We even tried changing the type of plastic plates that we used. Not once could we convince ourselves that we were getting lifespan extension. When people burn years of their careers trying to reproduce bad data, that has an impact, and it's very disheartening, at least to these individuals. When you look across all of the data in the literature, the net effect of resveratrol is... My name is Matt Kaeberlein, and welcome to the OptiSpan YouTube channel. Hey everyone, welcome to the OptiSpan podcast. So I've gotten several requests to do an episode on resveratrol, and so today's the big day. Here it is. You may have heard me refer to resveratrol as the most debunked longevity molecule in history. I think that's true, and so I thought what I'd do today is start by actually showing you the data that I believe supports that statement, and then I'm going to take you back in time to around 2003 and really give you a detailed insider's view of how the whole resveratrol story started and some of the, I think, interesting twists and turns that I was actually involved in along the way. So resveratrol, of course, is a naturally occurring molecule that's found in the skin of many plants, including grapes and blueberries and raspberries and even peanuts. But most famously, of course, resveratrol is found at low quantities in red wine. And it became hugely popular in the early 2000s, really based around the idea that resveratrol could slow aging, and then, by extension, red wine could have a positive impact on the aging process, which for obvious reasons is appealing to many people. Unfortunately, as we'll get into, that entire story was really built on a test tube artifact, along with some slick marketing and a fair amount of what I would characterize as shoddy science. So again, I think today resveratrol really has the dubious honor of being the most debunked anti-aging molecule in the world. And as I'll show you, dozens, maybe even hundreds of studies have tested the effects of resveratrol on lifespan across many different organisms, with the net result of the published studies being a 0% effect on lifespan. And I would suggest that due to publication bias, and what I mean by that is studies where a negative result is found tend not to get published. The actual effect on resveratrol across all of the experiments that have ever been done is probably a shortening of lifespan. So I want to be clear, I'm not suggesting or claiming that resveratrol has absolutely no health benefits in certain contexts. I don't know the answer to that. It's certainly possible that it does. But I also think it's worth mentioning that there's accumulating evidence that resveratrol can be harmful in certain cases, and there are persistent questions around bioavailability and quality of resveratrol supplements. And so for sort of all of the reasons that I'm going to get into today, I personally don't recommend resveratrol. I don't take resveratrol because I really don't think there's a clear benefit. And again, the preponderance of bad science in this area really makes me hesitant to draw any strong conclusions about resveratrol one way or the other in terms of the possibility that it may have health benefits for certain people. Okay, so regardless of potential generic benefits, the purposes of today's podcast is to really look at the claims around resveratrol as a longevity intervention. And again, I would suggest that we can say with a high degree of confidence that resveratrol is not a longevity molecule, unless perhaps with the exception that you are a nematode worm. And so let's start by quickly taking a look at the data that really support that assertion. And again, then I will take you back in time to when this whole story started. Okay, so I think the most convincing single study around resveratrol is a meta-analysis done by Alexei Moskalev and colleagues in 2022. And the title of that paper is Targeting Aging Mechanisms, Pharmacological Perspectives. And I like this study because the authors really asked a very simple question. And that question is, if we look at, basically all of the published experiments where drugs were tested for their effects on longevity, and in this case, they limited it to studies for drugs that have been tested at least 5 times, so 5 independent peer-reviewed articles. If we look at all the molecules that meet that criteria, what is the distribution of reported lifespan results look like? And to do this, they utilized the largest publicly available database for longevity interventions. It's called DrugAge, and took the data from that. And if you're a consumer of the OptiSpan podcast videos, you probably will have heard me say before that I really tend to weight data from unbiased studies over data from studies where it's clear that the authors went in looking to get a certain result. So that's one of the reasons why I like this study, because they didn't go in with any preconceived notions about resveratrol or any other molecule. They really tried to look as broadly as possible at the data that's out there and just ask the question across all of the molecules that are in DrugAge, what does the distribution of reported lifespan results look like? And so, as I mentioned, DrugAge is publicly available, so it's open access, which means the data is available to anyone on the internet. And you can, and I would suggest should, go and download the data and convince yourself that the conclusions I'm telling you about are correct. That's one of the nice things about having these sorts of open access tools that are available to anybody in the community. So according to DrugAge, resveratrol is the most widely tested drug in the literature, and rapamycin is the second most widely tested drug. And so this actually gives us a nice comparison point where we can look at the results from resveratrol first and then look at the results for rapamycin and compare and contrast. And I would say the comparison is pretty telling. So this graphic shows you, and this is from one of the figures in the paper, this graphic shows you the average lifespan effect for each individual peer-reviewed publication where resveratrol was tested. And so this is 169 experiments across 29 unique peer-reviewed publications. And this is a typical box plot. So the average effect is the solid horizontal line, and the individual dots are individual experiments. And so what you can appreciate here immediately is, first of all, there's a lot of variation. So we see that there's are ranging from 70+% lifespan extension to 35 or so percent lifespan shortening when we look across each of the individual reports in the literature. But the average effect when we take all of the data in the literature, those 169 experiments, is that solid horizontal line right on 0. So again, this is what I was alluding to a moment ago, that when you look across all of the data in the literature, the net effect of resveratrol is a 0% effect on lifespan, with a lot of variation around that. Now, it is worth saying that the largest positive effect, as I'm going to tell you in a moment, is actually an artifact and not real. And in fact, a couple of the other large positive effects come from the same yeast study or a subsequent study from the same lab. They are not real. So those should actually be taken out of this data set. And as I will suggest, those papers should actually have been retracted, but they weren't. So I would argue that the effect, even if we take those out, is going to come down a little bit. And then many of the other positive lifespan results here come from studies done in the nematode Caenorhabditis elegans. That's the one organism where I believe that resveratrol, at least at certain doses, can have a positive effect on lifespan. So that's driving some of the apparent effects of resveratrol here. Now, as I mentioned, I think there are a lot of data points missing from this graphic. In fact, I know there are because I did some of those experiments. It is often the case that when a lab does an experiment, if they get a negative result, so they see no effect, or in the case of resveratrol, they see a negative effect on lifespan when they are expecting to see a positive effect, those results never make it into the literature. First of all, it's hard to publish negative effects. And secondly, when you are trying to publish a negative effect for something that had been previously published to have a positive effect, that is even more difficult, and many authors are hesitant to do that because they are afraid of upsetting the authors who published the positive effect that, in the case of resveratrol, turns out not to be real. So I am quite confident that there are literally dozens of studies that never made it into the literature where resveratrol had a 0% effect on lifespan, or actually shortened lifespan. So that also makes me quite confident that if those data points were here, we would actually see that the sum total of results for resveratrol for all the experiments that have ever been done would actually lead to a negative effect on lifespan. But regardless, let's just accept this as it is. Resveratrol has no effect on lifespan when you look across all of the published literature. Again, this comes from Drug Age, so this is nobody coming in with an agenda here. This is just what the data show when we take all of the published experiments that are in the literature. Now, the authors of this study, of course, did not only look at resveratrol, they also looked at the other interventions that had at least 5 independent publications reporting lifespan data, and they summarized some of those in a single graphic. And so the next most commonly tested drug is rapamycin. That's now shown here next to resveratrol. A couple of things to immediately appreciate. The distribution is much tighter for rapamycin, and it's all positive. So when you look across the literature, essentially all of the published results for rapamycin in any organism where it's been tested have been positive effects on lifespan. And we can see that the average across all of the published studies is also positive. It looks like it's about a 20% increase in lifespan when you take the average of all of the published studies of rapamycin. So a striking difference here between rapamycin and resveratrol. And again, if you've watched this podcast regularly, you'll probably have heard me say that one of the reasons why I really gravitated towards rapamycin and continuing to study it in my own lab is I like to study things that are real and robust and reproducible. And rapamycin fits those categories, right? And as far as I know, everybody who's tried to reproduce the lifespan benefits of rapamycin has been able to. So I think, again, this is a nice comparison of something that works from something that apparently doesn't work. And we can look across several other drugs as well that have been tested multiple times in the literature, and you'll see there's a range of distributions. So like rapamycin, vitamin E seems to be pretty consistent, have a pretty nice tight distribution, not a lot of variability. Epigallocatechin 3 gallate also seems to have a net positive effect on lifespan when you look across the literature, although there's at least a couple of studies where it's had a negative effect. And then you can see other things that are less impressive. Metformin is another one that barely, if you look across all of the published studies, barely has a positive effect. And again, many studies have reported no effect or a negative effect. So you can see there's quite a bit of variation. Again, this fits with the idea there's a lot of noise in the literature in the longevity space, which is why reproducibility and consistency is so important when we're really considering, what are the gold standards? What are the things that we really believe in to have a positive effect on longevity? Okay, so again, I'm not going to take you any more into this paper, but it's a great paper. Encourage you all to take the time to read it if you haven't done so already. But I think this is really, from my perspective, what justifies me saying that resveratrol is the most debunked longevity drug in history. It's the most widely tested molecule, and the net effect across all of the published studies that are in Drug Age, at least, is 0. Okay, so I think it's safe to say resveratrol does not generally extend lifespan and probably actually shortens it on average. Yet, despite this, you will still hear resveratrol talked about today as an anti-aging supplement. And just as an example, this ad showed up in my email a couple of months ago, which then led me to post this tweet on X. So that the ad shows this, smiling, happy woman with the words "aging like a fine wine," right? Of course, referring back to the whole red wine connection to resveratrol. And then it says, "What is resveratrol? Glad you asked. A natural substance found in red wine," that's true, Resveratrol mimics the effect of caloric restriction. That's not true. And is believed to support healthy cardiovascular aging and possibly longevity. Okay, they put possibly in there. They said believed to support. I suppose there are some people who believe that. I certainly don't think it is commonly accepted among cardiologists or people who study the biology of aging that resveratrol supports healthy cardiovascular aging. So I would say that's pretty much a lie and definitely not longevity. So this comes from Thorne, which prompted me to post this on X. So this is my post now. This showed up in my email, and I just lost all respect for Thorne as a supplement brand, peddling the most debunked anti-aging molecule in history as an anti-aging molecule. Is there anyone you can trust in the supplement industry? So I went right at Thorne. I feel pretty good about that tweet. Not too long after posting that, I got actually a pretty nice email from a colleague of mine who's at Thorne, basically agreeing with what I said and saying that their marketing department went rogue and they would take this down, which I guess they did. Although Thorne is still selling this product called Resveracel, which says target the effects of aging from the inside out and includes resveratrol along with an NAD precursor. So again, I think that this is pretty dishonest, the idea that resveratrol is targeting the effects of aging. And I really wish that Thorne and other supplement makers would be more honest about the situation here. So I'm not sure what to say other than that I personally wouldn't trust any supplement company that is selling resveratrol based on claims around aging. I don't actually think there's much evidence for claims around anything with resveratrol, but certainly not aging. And I've shown you the data so you can draw your own conclusions. So that's where we're at today. And you might be asking, well, how did we get here? And so what I'm going to do in the rest of this episode is take you back to really how it all began. And I'm going to give you an insider's view of how Brian Kennedy and I first figured out that something was rotten with resveratrol. So the resveratrol myth really started in 2003 from this paper that was published by Conrad Howitz out of David Sinclair's lab. And the title of that paper was Small Molecule Activators of Sirtuins Extend Saccharomyces cerevisiae Lifespan. So Saccharomyces cerevisiae is budding yeast or baker's yeast. I will talk to you a little bit about the idea of how we measure lifespan in yeast in a minute. But so the study actually was pretty smart conceptually in that what the authors did was developed a new assay to look for activators of sirtu or sirtuins. So sirtuins are a family of enzymes, and I'll tell you more about sirtuins in a minute, that are all named after a single yeast enzyme called sirtu, SIR2. Sirtu, that's where you get sirtuins. So it's a family of proteins, a family of enzymes that structurally all look like the yeast sirtu protein, and that's where the sirtuins get their name. And so this paper set out to try to find drugs that could activate sirtuins. And the reason for that it really goes back to my PhD thesis where Mitch McVeigh and I showed that if you overexpress the yeast sirtu gene, you could increase lifespan in yeast. And so this is the yeast replicative aging assay. If you saw the episode in the R files where I talked about how I first got interested in TOR and rapamycin, I went into some detail on how this assay is actually performed. So this assay really involves micro-manipulating daughter cells away from yeast mother cells and counting how many daughter cells can a given yeast mother cell produce before that cell undergoes replicative senescence. That's replicative lifespan. And so what Mitch and I showed was that if we took the sirtu gene in yeast and we put an extra copy in, so we genetically engineered those cells to now have 2 copies of sirtu instead of 1 copy of sirtu, we could increase lifespan by about 30%. So that paper was published in 1999. The title of that paper is the SIR234 complex and SIR2 alone promote longevity in Saccharomyces cerevisiae by two different mechanisms. There's a bunch of other stuff in that paper, but the take-home message here is that you take a normal yeast, you take out SIR2, so you delete the SIR2 gene, that shortens lifespan by about 50%. You put in extra SIR2, you double the amount of SIR2, and that increases lifespan by about 30%. So this was the evidence that SIR2 seemed to be an important regulator of lifespan, and that by turning up or turning down the dose of SIR2, we could increase or decrease lifespan respectively. And then a couple of years after Mitch and I published this paper, other people showed that if you took the worm version of SIR2, which is called SIR 2.1, or the fruit fly version of SIR2, which is called DSIR2, you could increase lifespan in those organisms as well. Now, those of you who are sirtuin aficionados will recognize that there's been some controversy around the worm and fly sirtuin work. I'm not going to get into that. I'll just say the yeast SIR2 result that overexpressing SIR2 has been reproduced and has stood the test of time. So that definitely is real. The worm and fly stuff, I think we still don't really know how potent sirtuins are as regulators of longevity outside of yeast. But at the time, I think most people believed that SIR2 and the SIR2, what are called orthologs, these versions of SIR2 in worms and flies, were longevity regulators. And so it made a lot of sense then to think, well, if we could genetically turn up SIR2 and increase lifespan, if we had drugs that could do the same thing, those should also increase lifespan. And that was really the conceptual idea behind this 2003 paper from David Sinclair's lab, was to come up with a way to look for drugs that would activate SIR2 or sirtuins as an entire family. Okay, so before I get into that paper, it's also worth describing the activity of sirtuins that we're interested in here. So it turns out that sirtuins are a very special class of proteins called NAD-dependent deacetylases, okay? So again, for the sirtuin aficionados, yes, there are also some cases where they can do other activities like NAD-dependent ribosyltransferase or other NAD-dependent ACEs, but for the purposes of today's talk, and for by and large what most people think is important in the literature, is this NAD-dependent deacetylase activity. And that actually was work that I played a small role in from Shinichiro Amai when he was a postdoc in the Guarenti lab, when he discovered this new NAD-dependent deacetylase activity. And so that paper was published in 2000, titled Transcriptional Silencing and Longevity Protein SIR2 is an NAD-dependent histone deacetylase. So again, just to give you the timeline, 1999, Mitch and I showed that you could overexpress SIR2 in yeast and increase lifespan. 2000, Shin discovered this new catalytic activity for SIR2 and the human sirtuin, SIRT1, as an NAD-dependent histone deacetylase. I think it was 2001 when Heidi Tissenbaum showed that the worm sirtuin could increase lifespan in worms. So that sets the stage for this 2003 paper that we're going to get into in a minute. So to take you back, though, to this NAD-dependent deacetylase activity, this was really important discovery at the time because this was a brand new enzymatic activity, brand new chemical reaction that had never really been described before, where NAD was actually consumed in order to regulate epigenetically which genes got turned on or turned off. And I'll explain to you how that works in just a second. But again, for those of you who are sort of, maybe new to the field and really excited about epigenetic reprogramming and epigenetics and aging from the DNA methylation perspective and the clocks, this was really a much earlier, really first mechanistic demonstration of how epigenetic control of gene expression can regulate lifespan. Okay, so how does this NAD-dependent deacetylation activity work to control gene expression? So we'd known for many years at this point that SIR2 in yeast functioned to control the expression level, the volume of certain genes. In fact, that's where the name SIR2 comes from. SIR2, SIR2, actually stands for Silent Information Regulator 2. The silent part there means that SIR2 silences or turns down the expression of certain genes at certain locations in the genome. So again, I'm sort of going like this. You can think of SIR2 as the control knob, the volume knob for how high or how low certain genes get turned on or turned off. And in yeast, we knew that SIR2 had this effect, at least in very specific regions of the genome, the ribosomal DNA, the telomeres, and something called the heterophthalic mating loci or silent mating loci. So that's a very yeast-specific thing. But the point here is that SIR2 could turn up or turn down genes that were located in those parts of the genome. And again, if you think back and remember the central dogma, okay, DNA to RNA to protein. So DNA is where the gene resides. And what SIR2 is doing is it's affecting how much of that gene, the DNA, into RNA conversion is happening, right? So that's the transcription step. And SIR2 is a transcriptional regulator. It turns that step up or turns that step down for specific genes. And then that, of course, impacts how much of that RNA is made and therefore how much of the protein, which is the action, right, the machine that's actually doing the work, ends up getting made. So you can think of SIR2 as functioning at this arrow between DNA, the gene, to RNA. Okay, again, SIR2 is at very specific locations in the genome, ribosomal DNA, telomeres, and silent mating loci. And if we go back now to my PhD thesis work on SIR2, if we took out SIR2 from the yeast cells, we could get more silencing, in other words, lower gene expression at genes located near the rDNA, the telomeres, or these silent mating loci. And if we overexpressed SIR2, if we turned it up genetically, we would get more silencing, meaning less gene expression, less RNA, less protein. Okay, I'm taking you through all of this because it's going to be important as I lay out the story for how resveratrol was described as a SIR2 activator, and then how we and other people figured out that that really, at least in cells, in vivo, wasn't the case. Okay, so SIR2 increases lifespan if we turn it up in yeast, decreases lifespan if we turn it down, increases gene expression if we take SIR2 out of yeast, decreases gene expression if we turn it up, at least at these very specific loci, and SIR2 was an NAD-dependent deacetylase. But this is the thing. Nobody knew how SIR2 was affecting gene expression until Shin showed that it was an NAD-dependent deacetylase. And the histone deacetylase part here is what really is very cool and actually makes perfect sense once Shin figured it out. So histones are the proteins that package the DNA. So you can think of them as kind of wrapping around the DNA, and they control how tightly or loosely the DNA is packed. And when DNA is packed really tightly, that's hard for the transcriptional machinery to get in there and convert the DNA into RNA. So tight packing of the histones is like turning that volume knob down. And when the histones are packed loosely, more spread out, it's easier for the machinery to get in there and turn on those genes, convert it to RNA. And so what SIR2 is doing is it's taking a very specific chemical group off of the histones called an acetyl group, that's the deacetylase part, which then causes the histones to become more compact and reduces gene expression. So from a biochemical perspective, this was really neat because it showed that it explained why SIR2 was affecting gene expression through this chemical reaction that made perfect sense. The reason why nobody had ever figured this out before, though, was the NAD part, because histone deacetylases had never previously been connected to NAD, so nobody thought to include NAD in the reaction mix when people were trying to get SIR2 to act like a histone deacetylase. So it was a very cool story. I actually feel very fortunate to have been in the Garenti lab at the time that this was getting figured out. It's one of those, I think, very special experiences in science where it's this complicated mystery and you're trying different things, and then when you get the answer, you're like, oh my God, this is so cool. So it was great, and Shin was amazing in actually getting this figured out. Okay, so taken all together now, we knew at that time SIR2 acts to turn down gene expression by removing these acetyl groups from histones. And this connection to NAD was it consumes a molecule of NAD in order to do that chemical reaction. Okay, so this is the reaction here. And I want to draw your attention to the backbone of the histone here. So histones are proteins. They are a connection of individual amino acids linked together, and each amino acid has its own side chains. That's the R's here, R1, R2, R3. So one type of amino acid is lysine, and lysines can be acetylated. And what sirtuin does is it takes that acetyl group off of the lysines, and in the process consumes NAD. That changes the conformation of the histone into a state that reduces gene expression. So the acetylated state is the on state, the volume knob is turned up. The deacetylated state is the off state, the volume knob gets turned down. Okay, so this is the chemical reaction of sirtuin, as well as the human version of sirtuin, which is sirtuin. And again, for the sirtuin aficionados, yes, you could argue sirtuin is maybe more the human version of sirtuin. Doesn't really matter for the purposes of today's conversation. Okay, so now back to the 2003 paper from David Sinclair and colleagues. Again, at the time, we knew that sirtuin and sirtuin were NAD-dependent histone deacetylases, and they set out to create a cool workaround that would allow them to screen a large number of small molecules to find drugs that could enhance this NAD-dependent deacetylation reaction and make it go faster. That was essentially what they were after. And so in order to do this, they had this very smart idea of utilizing an artificial substrate. So if you think back to that histone, that acetylated histone that I showed you, that's not pragmatic to actually use in the context of a biochemical reaction in the laboratory where you want to measure the speed of reaction. It's just not doable at any reasonable scale. So if you want to screen for drugs that increase that activity, you need something that can be measured more quickly. And so what they developed was something called a fluorescent assay, where they could measure the amount of light given off, which can be done in high throughput, to identify drugs that increase that reaction. And so to do this, they developed this artificial substrate, so no longer that histone protein, but an artificial substrate with something called the Fluor de Lys, okay, which is a play on the French Fleur de Lys. Okay, so the way this Fluor de Lys assay works is it's an artificial substrate that they can mix with sirtuin, has this fluorescent group on it, and when sirtuin takes the acetyl group off of that artificial substrate, that changes the conformation in a way that the fluorescent group will give off more light, which you can measure in a high throughput way with something called a plate reader in the laboratory. So this suddenly allows you to start screening dozens, hundreds, in principle thousands or tens of thousands of molecules to find things that speed up or slow down this chemical reaction or otherwise change the various reaction parameters of this biochemical reaction. Okay, so it's very smart, very cool assay that opened up avenues to identify small molecules, activators, and inhibitors of sirtuins. And what they showed in this paper is that resveratrol and a few other structurally related compounds using this Fluor de Lys assay could speed up the rate of reaction. So that led them to believe that resveratrol was an activator of the NAD-dependent deacetylase activity of sirtuins. And specifically, they tested sirtuin and sirtuin and reported that resveratrol could activate deacetylation of the Fluor de Lys substrate by these enzymes. And so here's the data, and what you can see is that for sirtuin, resveratrol seems to be a pretty potent activator, up to about 8-fold increase in activity at 200 micromolar resveratrol. For the yeast sirtuin, it's a lesser effect, so the magnitude of effect is only up to about 2-fold at a lower concentration of resveratrol for the Fluor de Lys substrate. They also created a histone peptide with a different fluorophore. It's still a fluorescent-based assay, and reported an even smaller effect of about 1.5-fold for yeast sirtuin. But nonetheless, they interpreted this to suggest that resveratrol can at least activate sirtuins towards this substrate in vitro. So then the question is it actually having any activity in cells and what we call in vivo, in the real biological context? Now, they didn't show that from a biochemical perspective in this paper, but what they did go on to show was that resveratrol could have effects on lifespan and sirtuin-dependent silencing in yeast. And I'll show you that data in a minute. Before I do, though, I just want to note one thing for you, which is to look at the structure of the Fluor de Lys substrate compared to a real substrate, a real histone protein in cells. And you can immediately appreciate these things are completely different. So structurally, the Fluor de Lys substrate really looks nothing like the real substrate that sirtuin or sirtuin are acting on in cells. And that'll be important as we go throughout the rest of this video. So the question, though, of course, is, does resveratrol activate sirtuin in cells, in vivo? And so again, they're using first the yeast replicative lifespan assay, because remember I showed you that Mitch McVeigh and I had already demonstrated that if you overexpress sirtuin genetically, you can increase lifespan by about 30%. And what they reported here was a whopping 99% increase in lifespan from the cells that resveratrol was added to. They also made the claim that resveratrol was acting by a mechanism similar to caloric restriction, because when you add caloric restriction on top of resveratrol, you don't get any further increase in lifespan. And I'll come back and talk about this caloric restriction resveratrol sirtuin connection in a minute. The reason why they did this, I think, was because at this time, people still were working under the model that caloric restriction was working through sirtuin. So again, the model that had been proposed, it turns out that model is wrong, or at least incomplete. But at the time, the model that had been proposed was that caloric restriction was acting upstream of sirtuin and activating sirtuin by increasing NAD levels to increase lifespan. So a linear pathway, caloric restriction, sirtuin, lifespan. So they thought that if resveratrol was activating sirtuin, it should also work similarly to caloric restriction. And so the interpretation here is that because when you combine caloric restriction with resveratrol, you don't get a further increase in lifespan. That's consistent with the idea that resveratrol and caloric restriction are acting through the same mechanism. It's a little bit of a side story, but it turns out to be important when I talk about how Brian and I figured out some of the problems with this paper. Okay, so they claim a nearly doubling of lifespan, and that was pretty striking. So this, I think, is still the largest lifespan increase that's ever been reported in the yeast aging system from a single intervention. And as I mentioned, it's much larger than the effect that was shown for doubling the expression of sirtuin, which was closer to 30%. So this was a big, big effect and very impressive. So the other claims from this paper were, I already mentioned, activation of sirtuin and sirtuin towards the Fluor de Lys assay, activation of sirtuin in vivo as shown by increase in lifespan of up to 99%. They also reported increased telomere silencing and rDNA silencing, and I'll show you those assays in a couple of minutes. And then they also proposed that resveratrol and caloric restriction were acting through the same pathway. So that really was the take-home messages from this paper that was published in 2003. Okay, so now how did I start thinking about resveratrol and studying resveratrol? And this really goes to some work that Brian Kennedy and I were doing around the idea that sirtuin and caloric restriction were acting in the same pathway. And so again, to kind of give you a little bit of context, Brian and I were really much more interested in asking the question, if we look outside of sirtuin, what else can affect lifespan in yeast? And we started doing a screen through something called the yeast genome deletion collection, which is a collection of about 5,000 different single gene deletion mutants in yeast. And we were working in a strain called BY4742. And the reason we started working in that strain is because that's the strain that people had created the yeast deletion collection in. Up before that time, I don't think anybody had ever used this genetic background for yeast aging studies. And it turned out it was long-lived. And what we found was that sirtuin and caloric restriction seemed to act in different pathways, which disproved what was at the time the current paradigm in the field. And we published that in 2 papers. And the evidence for our belief that we had disproved this model really came from a couple of different key pieces of data. One is if we combined sirtuin overexpression with caloric restriction, and believe it or not, that experiment had not been done, despite the model that was in the literature at that point, and I'll tell you why in a minute. If we combined sirtuin overexpression with caloric restriction, we got an additive effect on lifespan. Now, that doesn't prove that sirtuin overexpression and caloric restriction are acting in parallel pathways, in different pathways, but it certainly is suggestive that they are. And I think the more definitive piece here is we could actually create a yeast strain where we took out not only sirtuin, but all of the other yeast sirtuins, and we could actually get a bigger lifespan extension from caloric restriction in that context, as long as we also took out a gene called FOB1 to block the damage that deleting sirtuin does at the rDNA. So taken together, I think these 2 results demonstrate that sirtuin and sirtuins in yeast are neither necessary nor sufficient to account for lifespan extension by caloric restriction. So that doesn't completely rule out the possibility that some small amount of the caloric restriction effect could be acting through sirtuins in some weird context somehow. It's almost impossible to completely rule that out. But Occam's razor, I think, would strongly argue that these 2 results together demonstrate that sirtuin and caloric restriction can act by different mechanisms and probably do act in almost every case, if not every case, through different mechanisms. And so that led us to propose this parallel pathway model where sirtuin acting through the rDNA, and I mentioned, if you recall, sirtuin silences genes in the rDNA, and caloric restriction acting through some other mechanism that I think we still don't completely understand in the field what that mechanism is. But then those converge ultimately to affect longevity. And I will say lots and lots of data since the time of our papers in 2004, 2005 have really backed up this model and solidified that this is very, very likely to be at least largely correct, to the extent that any model is ever completely correct. So we feel pretty confident and good about this model and the work that we did supporting it. So again, I think it's worth going into the weeds a little bit on how is it that we get to the point where we had a model that caloric restriction is acting through sirtuin, and how did we disprove it, and how does that tie into this whole resveratrol story? So this goes into one of the challenges, I think, with a lot of studies in invertebrate models and in laboratory studies is that people often work in their own inbred strains. I guess that's true in mice as well. I shouldn't have said invertebrates. And in yeast, there are a bunch of these different yeast strains where things can be different based on the genetic background. And so in the Guarenti lab, where I did my PhD work, I showed that you could overexpress sirtuin in the W303 strain background. And not too long after that, Suju Lin, who was a postdoc in the lab at the time, showed that caloric restriction could increase lifespan in yeast in a different strain background. So she wasn't working in W303. She was working in a genetic background called PSY316. So my paper came out in 1999. I think Suju's paper came out in 2000, working in these 2 different strains. But nobody outside of the yeast community is going to pay any attention to that. And what was not really appreciated really by anyone outside of the Guarenti lab and the Sinclair lab, because David came from Lenny's lab for a few years until Brian and I published it, was this sort of paradox that SIR2 overexpression increases lifespan in W303, but caloric restriction doesn't. And caloric restriction increases lifespan in PSY316, but SIR2 overexpression doesn't. And so the model that was proposed, that caloric restriction is acting upstream of SIR2 to increase lifespan, it's difficult to reconcile that model when SIR2 overexpression works in one strain background and caloric restriction works in another strain background, but neither of them work in both strain backgrounds. So that was a bit of a mystery until Brian and I started working in BY4742 because we were looking at the deletion collection. But one of the things we did first was to test known interventions to see which of those worked in this new strain background, because we thought it was important to know which interventions work in the strain background we're going to do this very large screen in. And we were pleased to see that both caloric restriction and SIR2 overexpression worked in BY4742. And by worked, I mean increased lifespan. So we could do that experiment of combining them, which nobody had ever done before. And lo and behold, we found this additive effect, which got us thinking, maybe the model that caloric restriction is upstream of SIR2 is incomplete. And so we went and did a whole bunch of experiments to, I think, disprove that model pretty convincingly. Okay, so why did we test resveratrol? And it's all because we were still trying to publish this new model that ran counter to what everybody in the field thought was the case, which was that caloric restriction was acting through SIR2. So we really felt like we needed to dot our I's and cross our T's and test this every possible way we could test it. And so we saw the paper from David's lab that resveratrol was an activator of SIR2. And we thought, okay, this is great. Now we have a small molecule that we can use to test this model a different way. We knew if we genetically overexpressed SIR2 and combined that with caloric restriction, we got this additive effect on lifespan in BY4742, where both of those interventions worked. We thought, great, we can use resveratrol as a small molecule activator of SIR2, and we should get the same result if our model was correct, where we got an additive effect on lifespan. And so we tried that experiment, and we could not get resveratrol to increase lifespan. We fully expected to be able to replicate the Howitz et al. Result when we started down this path. So we tried, and we tried, and we tried, and I mean, literally spent probably a year, maybe 18 months, trying all sorts of different ways to get resveratrol to work. And again, by work, I mean increase lifespan in our hands. And we tried BY4742, we tried W303, we tried PSY316, which was the strain used in the Howitz et al. Study, could never get resveratrol to work. We tried different suppliers of resveratrol, different forms of resveratrol. We tried it in the light, out of the light. We even tried changing the type of plastic plates that we used. Not once could we convince ourselves that we were getting lifespan extension, and certainly nothing close to what was reported in the Howitz et al. Paper, and not in any of the strains, not in BY, W303, or PSY316. So we then thought, okay, maybe there's something tricky about the lifespan experiment. Let's look at SIR2 activity in the cells using this silencing readout, right? Remember, again, SIR2 is turning down the expression of genes near the rDNA, the telomeres, and the mating loci. And so we had strains that had been engineered with what are called reporter genes located near the telomeres and in the rDNA. So we could measure the reporter activity of these genes to see were they turned up or were they turned down. And so we looked at this several different ways. One of the ways we did this was with a strain that had a gene called URA3, that's a gene involved in uracil biosynthesis, integrated near the ribosomal DNA, or actually within the ribosomal DNA array. And it turns out in yeast that if you have a strain that's expressing this URA3 gene, if you add the drug 5-fluoroorotic acid, or 5-FOA, to the media, that's toxic in the presence of URA3. So the more URA3 you have being expressed, the more poison the 5-FOA in the media becomes. And so you can use this as a readout of how much URA3 is actually turned up or turned down. And so in this case, what we did was we had a wild type strain, so single copy of SIR2, URA3 in the rDNA. We treated that wild type strain with resveratrol to see if we could get increased SIR2 activity, which should lead to less URA3 expression, more cells surviving in the presence of 5-FOA, okay? We had a control where we overexpressed sirtu, so we knew that should turn up silencing. That should give more survival in the presence of 5-FOA, which is what we saw. And we had a strain that was completely lacking sirtu, so we took out sirtu. That should turn down silencing, turn up URAT3 expression, make the 5-FOA more toxic. You can see all of the cells died when sirtu was deleted. No effect from resveratrol compared to the wild type cell not treated with resveratrol. So we couldn't see any evidence that resveratrol was activating sirtu as measured by readout of a gene located near the rDNA. We saw the same thing at the telomeres using a different gene called AD2. This is a gene involved in adenine biosynthesis. It turns out that when AD2 expression gets turned down, so more silencing expression gets turned down, you accumulate a red pigment in the cells that causes the cells to turn red or pink. So in this case, if we had more sirtu activity, we'd make less AD2. That would cause the cells to turn pink. And again, if you compare the wild type to the strain with an extra copy of sirtu, you can see that pink color show up. If you delete sirtu, you can see the cells get even whiter because they're making less of the pigment. And you can see if you compare the wild type to the resveratrol-treated cells, there's no difference. So again, using this telomere-based readout as well, we could not find any evidence that resveratrol was activating sirtu in vivo, even though both of our controls worked. So this made us pretty confident that resveratrol wasn't activating sirtu in our hands in vivo. And I think it's worth saying, Brian and I really tried everything we could to get resveratrol to work. We had multiple correspondences with David Sinclair. I offered to go to Harvard and do these experiments in David's lab with his people to see if they could help me figure out what we were doing wrong. We offered to have someone from his lab come to Seattle, do the experiments with us. David said he was too busy. And eventually we just got frustrated and we're like, okay, we're pretty sure that we're doing everything we can and that resveratrol does not activate sirtu in cells. And we'd really taken it as far as we could. And so really, again, it was probably 18 months of spinning our wheels. We were sort of stuck. It's worth saying, we could get the Fluor de Lys assay to work. So we could see activation of SIRT1 in a test tube using the Fluor de Lys substrate by resveratrol. We just couldn't find any evidence it was actually doing anything to sirtu in yeast cells. And we were using exactly the same resveratrol stock that worked in the test tubes, did not work in yeast cells. And so we were thinking about publishing this story, and we had one more idea that we thought we should test. And we thought maybe it had something to do with the Fluor de Lys assay itself, that fluorescent substrate. So we decided to go through the heavy lift of actually testing something closer to a real substrate, something that looks like an actual protein that sirtu or SIRT1 might see in a cell in the test tube. So replace the Fluor de Lys with a real substrate and see if we could see activation by resveratrol there. And so this is the data using two different peptides. One is a substrate of SIRT1 called P53, and another is this histone substrate, histone H4. And we tested two flavors, one with the Fluor de Lys group and one without the Fluor de Lys group. Everything else is identical here. And it was pretty striking. When the Fluor de Lys group was on there, you see this very, very steep activation of SIRT1 by resveratrol. When the Fluor de Lys group is taken off, nothing. Resveratrol does absolutely nothing to this chemical reaction. And so to us, this was pretty convincing that the resveratrol activation is an artifact caused by the Fluor de Lys group being on there. You take it off, you no longer get activation. So to us at this point, the resveratrol story was pretty much told. The activation of SIRT2 and SIRT1 by resveratrol was an artifact of the Fluor de Lys assay. And really, that's pretty much as open and shut a case as you're ever going to get in science. So we published the paper. I think we were actually probably too generous in the title of the paper. We titled the paper Substrate-Specific Activation of Sirtuins by Resveratrol. It was published in the Journal of Biological Chemistry in 2005. This title, substrate-specific activation, the reason why I say it was too generous is, while technically true, resveratrol can activate sirtuin towards certain substrates that have this Fluor de Lys group on it. We didn't have any evidence that resveratrol could activate sirtuin towards any other substrates, and I think we were pretty confident that, in fact, resveratrol did not activate sirtuin or sirtu towards any biologically relevant substrates. Nonetheless, we did leave the possibility open that there might be certain proteins in certain contexts in certain cells where resveratrol could, in fact, activate sirtuins to deacetylate those proteins more efficiently and effectively. That's why we had the title substrate-specific activation. Okay. It was pretty interesting because in the very same issue of JBC, a different lab, John Deneu's lab, completely independently of us. Really, we had no interaction with the Deneu lab prior to these papers coming out about this story, published a paper that basically reproduced all of our conclusions. The title of that paper was Mechanism of Human sirtuin Activation by Resveratrol. Again, they were extremely generous in the title of their paper as well. Again, that probably was a mistake and may have contributed to the ability of this resveratrol story to continue to dog the field for as many years as it has. So I'm not going to take you through this paper from the Deneu lab, but I do want to read a couple of excerpts from their abstract that I think are pretty telling. One is, among the 3 enzymes tested, so they tested 3 different proteins, yeast sirtu, human sirtuin, and another human sirtuin called sirtu2, only sirtuin exhibited significant enzyme activation, approximately 8-fold, using the commercially available Fluor de Lys kit. So they could reproduce the activation of sirtuin by resveratrol using the Fluor de Lys substrate. They could not show any activation of yeast sirtu, even using that Fluor de Lys substrate. So again, going back to the inability to find significant activation of sirtu in cells, when Brian and I tried to do those experiments, this is supporting our data that resveratrol actually doesn't activate sirtu in cells because it doesn't even activate sirtu in a test tube when using the Fluor de Lys substrate. The other thing I want to point out that they said is, although sirtuin activation was independent of the acetylpeptide sequence, resveratrol activation was completely dependent on the presence of a covalently attached fluorophore. So again, just like what we saw, if they took that fluorescent group off, no more activation by resveratrol. Again, strongly supporting the idea that this was all a test tube artifact due to the presence of that fluorophore on the substrate. Okay, so again, the Deneu paper independently confirmed that activation of sirtuin by resveratrol appears to be a test tube artifact, and that resveratrol does not activate yeast sirtu, apparently in any context, Fluor de Lys or no Fluor de Lys. So I think altogether this really raises a kind of disturbing question of how did the Howitz et al. Paper find a nearly 100% increase in lifespan that they reported? And I don't know the answer to that. There really is no reasonable explanation. And from a purely statistical perspective, the likelihood that you would get a result that far off from the true value by random chance is much less than 1 in a trillion. So this is still an open question as to how they actually got that result. And this all happened back in 2005. Really, in any reasonable world, that should have been it. Given the obvious artifactual nature of the findings, in my opinion, the 2003 paper should have been retracted at that time and removed from the literature. That didn't happen. And instead, we got more than a decade of hype, I would say damage to the reputation of the field, and probably harm to the health of millions of people who were sort of tricked into believing that red wine was good for them. And that all came about because instead of a retraction, what we got was a paper published in 2006, also from the Sinclair lab, which is now kind of infamous, where they claimed that resveratrol increased lifespan in mice, which got a lot of attention, as you might imagine. It turns out it doesn't. And that has also been fully debunked by multiple groups, including the National Institute on Aging Interventions Testing Program, which showed that resveratrol treatment in normally aging mice has no effect on lifespan. So that paper actually was titled Rapamycin, but not resveratrol or simvastatin, extends lifespan of genetically heterogeneous mice. So we can be pretty confident that resveratrol does not increase lifespan in mice. What the 2006 Sinclair paper that really fueled the fire here actually showed is that resveratrol might partially suppress the toxicity associated with a 60% coconut oil diet fed to mice. So this is it's a weird diet. I don't actually know how they settled on this formulation, but it actually causes the liver of the mice to become so fatty and so enlarged that it impairs the function of the lungs and impairs the ability of the mice to breathe, and they have a dramatic shortening of lifespan. And in this study, resveratrol seemed to increase median but not maximum lifespan of the mice fed the toxic coconut oil diet. I say might here because as far as I know, nobody has reproduced this particular experiment. And honestly, I've gotten to the point where I trust nothing from certain labs until it's been independently replicated. So I don't know whether that's a real result or not. Regardless of whether the coconut oil toxicity benefits are real, I think everyone who's being honest at this point agrees that resveratrol likely does not impact longevity in the context of normal aging in mice. And as we saw earlier from the 2022 meta-analysis, this also seems to be true across all of the published experiments in all of the organisms where resveratrol has been tested. Okay, so that brings us now back to 2024. And I think it's reasonable to ask, why is it that so many people still believe resveratrol has anti-aging or general health promoting properties? Certainly the sexiness of the red wine story has played a big role here. And I think it's fair to say that there's been a concerted and ongoing effort by certain people to keep this myth alive, probably for self-promotion and financial incentives. Right around the time of the 2006 paper, David Sinclair co-founded a company called Sirtuin based on the resveratrol story. That company quickly went public and then quickly was sold to GlaxoSmithKline for $720 million. And then just a couple of years after that, Glaxo shut down the entire Sirtuin program, which honestly was not surprising at all to many of us who were in the know because we'd lived through this whole thing, as I've just told you about. Looking back, I think it's fair to say that the resveratrol saga is likely the most damaging mistake the field of geroscience has ever experienced. Without a doubt, in my mind, the loss of $720 million by Glaxo sent a chill through Big Pharma that likely delayed re-entry into the field by more than a decade. I think we still haven't really seen Big Pharma start to come back into the field. Maybe we're starting to see the first indications of that. And I think it's, literally hundreds of millions of dollars of grant funds have been wasted trying to follow this story up. And, maybe even worse than that, many trainee careers have stalled by trying to reproduce data or trying to test a model that just isn't reproducible. And again, that you may think I'm being dramatic, but I've talked to a lot of these grad students and postdocs at conferences and when I go give seminars, how they have been trying to follow up on the resveratrol story or the sirtuin activating compound story. And, when people burn years of their careers trying to reproduce bad data, that has an impact, and it's very disheartening, at least to these individuals. And so I think these are often underappreciated consequences when bad data gets in the literature, and it takes a long, long time for the literature to work itself out. I also think, it's worth at least talking about, but harder to calculate, how many lives were damaged by people buying into the, miracle molecule in red wine story. So obviously there's personal responsibility when it comes to overconsumption of alcohol or red wine. But when Harvard Medical School backs the idea that red wine is anti-aging, you can't completely fault people for buying into that. If I'm being completely honest, I even kind of used this story as an excuse to drink wet red wine, and I knew the whole thing. So I think it is, it's a real thing that a lot of people were enticed to drink more alcohol than they otherwise would have by the idea that red wine is anti-aging. And honestly, I think Harvard has some responsibility here, both for helping to fuel this idea that red wine is good for you and by not cleaning the story up when it became clear that it wasn't true. And, I think it's unfortunate. So really, this just illustrates in my mind how damaging bad science can be when the authors and the institutions don't step up and take responsibility for misleading the community, especially when it's in an area that is easily hyped and can influence people's behaviors in unhealthy ways. So we're now 21 years out from the initial resveratrol artifact paper. I think the scientific community, by and large, knows the story is mostly false. I think only a few people are really still studying resveratrol, at least in the context of longevity or sirtuins in any real way. Yet the supplement industry still uses the lie that resveratrol targets aging to sell their products. As another example, Tally Health, another company started by David Sinclair, actually includes resveratrol in their supplements. So they sell you a test, and then they tell you to buy their supplement, which includes resveratrol, that, quote, slows aging at the cellular level, which, as I've shown you, is just not true. The data don't back it up across the entire field, and yet they're making these claims, which is dishonest. So I don't know what else to say about that. You can draw your own conclusions, but I think it's kind of disgusting. Overall, I really hope the field can learn from this and avoid making the same mistake in the future. Those who don't learn from history are doomed to repeat it. Hopefully we can learn from history. And if nothing else, hopefully I've given you all a better understanding of the real story around resveratrol, and that this can help you make your own decisions and apply critical evaluation to some of the claims out there in the longevity space. So as always, thanks for watching. I hope you found this useful and informative. Please, again, feel free to leave comments, ask questions. If you're not a subscriber, consider subscribing. And I hope to see you next time on the OptiSpan podcast.